Hello, everyone. Good afternoon. Welcome to the Engineering in Space session. My name is John Chinner, and I'm an engineer with a company called Airbus Defence and Space. And I'm joining you from my log cabin office slash workshop at the bottom of my very soggy garden in Hampshire. And I am joined today by some very interesting people from the world of space engineering. I've got a electronics engineer, a dynamic modeler, and a senior deep space mission operations engineer in the room with us right now. I'm really excited to talk to these people. So I will let them introduce themselves. You've heard enough about me already, so I'll let them introduce themselves. So firstly, over to you, Barry.
Hi there. I'm Barry Whiteside. I'm an electrical engineer, and designed and helped build the electronics for the ExoMars PanCam instrument that's going on the European Space Agency rover. And so I'm here in the electronics lab at the Mullard Space Science Lab at UCL.
Thanks, Barry. Very interesting. Love your backdrop, and I've been assured that's definitely real. That's where you work.
It is indeed, yes, real, and yeah, things move.
Brilliant. And Charlie, tell us about yourself.
Hi, I'm Charlie. I'm work at the National Satellite Test Facility at a place called RAL Space, and I am involved in the sort of dynamic testing of spacecraft. We shake them because you've got to survive the launch, which is quite violent. And we test things from small pieces of equipment up to minibus-sized, full-size satellite. So yeah, that's me.
Perfect. So we've had someone who designs and builds things to go to space. We've got someone who tries to break them before they go to space, and we've got someone coming up, Jamie, who operates things when they are in space.
Hello, I'm Jamie Williams. I'm the Senior Mission Operations Engineer here at Goonhilly Earth Station. So my day-to-day job is working on missions like Mars Express, which we've done so today, and downlinking photos live from Mars and sending the telecommands up to tell Mars Express what to do, as well as working on other missions like landing rovers on the moon for Intuitive Machines in the last couple of weeks, and our mission, what we're operating right now on the dish behind me, for the Indian Space Research Organization, the Aditya spacecraft, which is studying the sun at Lagrange point 1. So I participate in operations as well, but other miscellaneous engineering and R&D and CAD tasks here at Goonhilly.
Brilliant. Brilliant. So I'm going to pick up a conversation with each of you about some of the things you're doing in space and then a little bit more about your career points. But if I can go first to you, Barry, can you tell us a little bit about something you're working on, something you've done, something you're really, really excited about, and you can tell us all about it, and maybe you've got something to show us.
I do indeed. So here I have a model of the PanCam imager that we've built for the European Mars rover. So this is effectively a suite of cameras mounted inside this optical box. And we have a camera here, another camera here, and one over here. And so really this is acting as like the science eyes of the rover. And so by imaging with the two cameras that are separated, acts a bit like your eyes. And so it gives us useful depth information about imaging when we're taking images on Mars. And then this camera here is what we call our high resolution camera. You can see it has a bigger aperture than the other two cameras. And that's to allow more light to look in, to collect more light. So we can look in detail at the rocks and see what textures and what colors these minerals are on Mars. And so I helped the team. We were a very large team that built this camera. So we had parts coming from Switzerland, we had parts coming from Germany, and then parts in the UK as well. And I was responsible for helping put it all together, test the electronics, design any cables, and make sure that the power interface and things like that all behave as expected, so that when this unit is placed on the rover, we're confident it's going to work. And we're also very confident that it's going to survive not only the launch, but the journey to Mars and then the landing as well.
Brilliant. So you actually had your hands on and part of the build of the actual flight PanCam for the ExoMars rover. It came through the Mullard lab and you built it there and you shipped it off as a complete assembly. You actually had your hands inside there.
That's right. But one of the things, certainly for the one going to Mars, we had to be really careful not to contaminate it. So although I had kind of my hands on it, I had to have 2 layers of gloves to make sure that I wasn't going to contaminate it with any bacteria. Because one of the objectives of our rover going to Mars is to look for signs of life and see. And the one thing we definitely don't want to do is contaminate it with our own bacteria or viruses or biological life, because otherwise that might contaminate any samples we take on Mars.
Yes, we don't want to go all the way to Mars and look for signs of life and find some little organic bacteria or microbe that came from Stevenage. That's certainly something we don't want to do.
Exactly. Yeah.
So I imagine it's pretty exciting for you then, thinking that obviously that work is done now. You've built that flight piece of hardware. You've shipped it off. It's been integrated with the rover. We're now waiting for the rover to finish its processing, a new landing platform and all those things to happen so we can get that rover to the surface of Mars. But what will you feel like when you see those images of either the rover taking photographs of the surface or the rover in operation, knowing that your handiwork is there on the surface of Mars?
I honestly can't wait. That's the most exciting bit. I'm going to clear a nice big empty space on my fridge to have that first image just sellotaped on there whenever we first get it. So yeah, it's a long way. I think we're expecting it to be the year 2030 by the time we land on Mars, but there's plenty to do in that time. We have to plan all our operations and work out how we look after this instrument on another planet 24/7. So yeah, plenty to do, but yeah, exciting end goal for sure.
Amazing, it's brilliant. And I suppose there's a nice little intro to go to Charly then. So you've built something to go to Mars, and Charly would take these spacecraft, pieces of spacecraft, entire big minibus sized spacecraft, and Charly, you would be testing them before they go to space to check that they're not going to break on the way or break when they get there. So can you tell us a little bit about all the things you do with regards to spacecraft testing?
Yes, actually, there's quite a lot of different types of spacecraft testing. We usually test to make sure that it will function in the same way. One big thing we have, which takes quite a long time, is what's called a thermal vacuum chamber tests, which giant big, well, again, it varies depending on the size of things, but it is, as they say, it sucks all the air out, so produces a vacuum, and then will regulate the temperatures up and down to sort of mimic the life in space. So that's sort of testing to make sure that the object spacecraft will survive its kind of life in space. But that is kind of what colleagues do. I personally involved in what we call dynamic testing, which is when it's moving, which is largely simulating the launch, which is quite a short period of life, but is incredibly violent. If you've seen any videos of launch, they're very loud, and you know, the air and the noise of it all is buffeting the rocket back and forth, which obviously the spacecraft inside also gets buffeted quite a lot, and all of those forces and everything can quite easily shake everything apart, from actually kind of the structure breaking, also just to the very fine soldering on sort of some of the beautiful electronics, for example, that Barry might have done. And you basically you don't want to find out that you've not done a great job of either putting a bolt in or doing a solder when it's in space, because it's quite hard to fix. So my job is making sure that if something's going to break, it breaks on the ground where it's easy to be fixed. As I said, so yeah, we test little pieces of equipment up to full-size satellites. Or we will. The new facility is still being built. That's kind of my exciting thing that I'm working on at the moment, is we're commissioning and making sure all of the new facility that can test these sort of the minibus size satellites, we can test them and get ready for our first customers by the end of this year.
Yeah, it's interesting. It goes to say about the different range of satellites that we have. So I've got this is like a CubeSat here, a 10 centimeter by 10 centimeter small satellite. And if I was to think about a satellite that the company I work for, Airbus, is building, like a Skynet, like you say, a minibus sized satellite from small to very, very big. And the tests have to be the same, I suppose, for all of those satellites.
The test concepts are obviously so we do kind of different types of vibration tests on, funnily enough, a shaker, because it shakes it. Engineering, we can be quite literal with naming things. So yeah, for something like that, it's the same concept. We'll have, whether it's, as you said, the small, kind of about this size, they will go through vibration. But then, yeah, again, sort of, as you said, yeah, Skynet 6, which is the next one, which will be tested here. That's kind of our first big one. We're looking forward to testing that from Airbus. Yeah, that is easily the size of like a big white van. It's huge. And yeah, but again, it's still, we bolt it to the shaker. Obviously, a lot more bolts that would be used for your sort of little CubeSat. And yeah, but actually the base kind of vibration that goes through those sorts of things on the surface is actually much less for the larger satellites. Reason being is that all the kind of the motion and the accelerations kind of at the base of that then gets stepped through, and then all the smaller pieces will then see higher levels. So then when we do what are sort of sub-assembly tests, they tend to be at higher sort of forces and accelerations.
So I'm assuming then, if you're going to put your satellite on a rocket and the rocket's below here, do you have to test that satellite in every orientation, or do you just do it in the one?
Yes, so we test in X, Y, and Z. The moment, pretty much all shakers are just test in one axis. So we have normally got a nice shaker. I'm just going to use a box that's on my desk. It tend to be square, and you'd attach your satellite at the top, and then it would go up and down. And then we have normally what's called a slip table, which then attaches here and then flip. So you sort of turn the shaker and then it would go back and forth. And then for normally that's kind of up and down is Z, and X and Y, you just attach it to the slip table in a different orientation to sort of take. There are coming up newer shakers that can test all three axes at once, but they tend to be extremely specialized because making sure that everything's being excited in the right way at the right in all of the axes is actually incredibly complicated.
Well, I happen to know you have a little tool with you to help you visualize how you would test a satellite in terms of the X, Y, and Z axes.
Yes, so I have a little wooden satellite with the axes sort of held on, so it's useful to remember which way they go around.
Yeah, so high-tech business that we work in, but sometimes low-tech methods work just fine.
No, absolutely, yes.
Perfect, brilliant. Thank you, Charlie. And let's go over to Jamie. I know you're in work today. Technically, you've been working probably all day on Mars Day down there, and lots of stuff going on. So tell us a little about what you're doing down in Goonhilly, Jamie.
So what we've been doing today, I've been mostly supporting the Mars Day presentations, and we started this morning setting up for Mars Express and starting to downlink photos and science data from the spacecraft and sending up the telecommands, which they go from the Mission Control Center in Germany through us at Goonhilly and radiated out the antenna towards the spacecraft. So it's been quite.
So you're pointing your dishes towards spacecraft millions of miles away out in space, and you're receiving signals from them and also transmitting signals back to them to operate those spacecraft in space.
Yes, yeah. We point the antenna slightly ahead of Mars as we're all moving, and then we send out high amounts of power with all of the telecommands to tell it what to do, whether to update its onboard schedule or to send back science commands back or plan the sequence of events for the next few days or weeks of that spacecraft.
So what does your day-to-day job look like then, Jamie? What do you actually do when you turn up at Goonhilly?
Day-to-day is working on spacecraft like around Mars or landing on the moon. It was quite an exciting, intense couple of weeks for supporting the Intuitive Machines commercial lunar lander, which we were Intuitive Machines prime ground station for supporting their lander and all of their burns to get them into the right orbit. And we were the first ground station for letting Intuitive Machines know that their spacecraft made it softly to the surface of the moon, albeit not at the right orientation. But yeah, happening right now behind me is we're supporting ISRO's Aditya L1 spacecraft, which we do pretty much every single day. But I get involved in other R&D tasks. One of the projects I've been involved in, which is expanded from my university dissertation, is designing the mechanical components for cryogenically cooled receivers for our large antennas. So on our second largest antenna and the deep space antenna behind me, designing super cold cryogenically cooled receivers to hopefully reduce the noise floor on our large antennas and give us a bit more of a margin for decoding more data from these spacecraft or spacecraft which are further away, where the signal is going to be much weaker by the time it gets to us.
Yeah, it was really exciting to see the IM-1 mission, so well covered in mainstream media, and seeing Goonhilly put right up there as the prime. I guess it's because of the nature of the way that where the moon was in the sky and where the Earth was. You were like the prime site that could point your dish at the moon at that time when they were planning on landing that mission. And if we were on the other, someone else pointing at the moon, they would have picked up that comms. I guess it's quite lucky, really, that Goonhilly was so forefront in that.
Yeah, we've been working with Intuitive Machines for a few years now, and I think they might have wanted a company which had some heritage in deep space communications. So we're very fortunate and privileged to be that prime ground station, responsible for getting that signal back and all of the data as well. They also had a large support from Parkes Radio Telescope down in Australia, which is a slightly larger dish than ours. It was 64 meters versus our 32. But we were able to get back a large chunk of the science data as well from that spacecraft.
It's amazing. It really, for me, shows that I know a lot of these news stories are covered internationally or multinationally, but the UK is right there at the forefront. A lot of these missions are happening that maybe we don't get our badge necessarily flown on a spacecraft or some part of the mission, but actually we're there right in amongst it, working on parts of that, really important. Now that spacecraft wouldn't have worked without some kind of data getting back to the Earth, right? So, being there and being part of that is really important.
Yeah, it's integral to have that space to ground segment to enable them to talk to their spacecraft or to be able to receive any data. It's all well and good to be able to launch a spacecraft into space, but if you can't talk to it, it's not much good.
Perfect. So hopefully the people listening in have had some insight into some people working in space in the UK and the different jobs that are available. But I guess we'd like to do a little bit around the group, just about your career aspirations. What you wanted to do when you were at school? What do you thought about what your future looked like? Because I think a lot of the people on the call today are young people at school themselves, and they want to maybe aspire to be like you in the future. So just quickly on me, I'm an ex-apprentice. I did a technician apprenticeship 20 years ago, and I've been working in engineering ever since. And since I was an apprentice, apprenticeships have become much more commonplace in space. And in Airbus Defence Space, where I work, we have nearly 20 degree apprenticeships now starting every year. So there's definitely a thing to look at if you wanted to join space. So Barry, tell us a little about yourself and how you got to where you are.
Sure. So when I was younger, I always loved trying to understand how things work and what things are made of. And I really enjoyed science. That was always my subject at school. And basically, I was never really sure what I wanted to do beyond that, other than like study and learn how things work. So I did A-levels in science, and then I went on to do a degree in physics. And in my final year project, again, I didn't really know what I wanted to do, but I just kind of knew the things that I might enjoy, which were a bit of programming, a bit of equations and analysis, and then building something and testing something with some electronics. And so I did a space project, and we were testing a new type of magnetic sensor. And kind of from then I was hooked. And like, even though I did my whole degree was in physics and I did very little electronics, because of the skills I'd learned during my degree, it was quite easy to apply to electronics. And although I had to learn from scratch again, I shifted to that. And for the last 10 years now, I've been working in electronics, but my physics background sometimes really helps me understand like how the system works and what are the important things to consider. And the other people I work with all have different skills and different backgrounds. And I mean, I really enjoy the team working in the space industry. And so by all of us having slightly different histories and backgrounds and different trainings, we all help each other out. So yeah, that's kind of my career to where I am today.
Brilliant. And Charly, I know that through your PhD, you did some work on vibration testing. So tell us about, that's very much of the current part of your life. But back when you were at school, what did you study? What did you want to do? And what were your aspirations?
When I was at school, I had absolutely no clue what I wanted to do. I mean, I enjoyed playing around, as Barry said, sort of building things. But to be honest, I didn't have great science teachers, and I didn't enjoy science that much. I actually really enjoyed history. So I went to university, did history. But then towards the end of that, I was trying to work out what I actually wanted to do as a job. Because it's one thing it's sort of studying something, I think, but then to actually kind of try and do it then for the rest of your life is a little bit more daunting. And I can't even quite remember how it came out. I thought actually, if I could do absolutely anything in the world, I thought building spaceships was actually kind of cool. So, luckily, I got a lot of support. I had to work quite hard, but yeah, I completely changed, pivoted, went from doing history, and stayed back at uni. Did a different course in engineering. And then from that was then very fortunate to be offered a PhD and remain studying. Probably stayed at university too long, but I did very well with it. And then now it is my job. I love it. But yeah, if you're not sure what you want to do, just do something you enjoy. And it isn't a kind of key thing. Obviously, as far as you guys are being to this is to the kids, you're being told to make all these choices when you're at school. You might get it wrong, but don't worry about it. You can change. I know people who've changed their careers, and they had a career for kind of decade or so, and then they've gone, actually, I don't want this, and they've changed completely. There will always be a possible thing, so don't worry about making the right choice. Just choose something that you enjoy. Would be the absolute thing.
It's great advice, and I think I talk to young people quite a lot, and I have a similar message to try and find something you enjoy doing. And sometimes it can be difficult to know what you enjoy doing. And my advice would be to go and find things, go and take on challenges, say yes to opportunities that come your way, and see what you might not have thought you enjoy. And like Charlie, you went off to university and did a degree in history, and then did a back-to-back degree in engineering on the back of it, and clearly you love both. So there you go. I guess it's a wonder what you can be motivated to do when you're passionate about something, for sure. And like you said, it was hard work. And Jamie, I'm assuming you're still there. I can't see you on my screen. I can see you on one of my screens. So I'm gonna ask you to speak now, Jamie, and I'm going to assume you're still there.
I hope you can see me.
No, there you go. I can still see you. Yes, you're back.
Yeah. So like the others at school, I had no idea what I really wanted to do. I went on to study at college something completely different to what I do today, forensic science. I wanted to kind of retain a bit of a science element. I never at that point thought about the space industry. I didn't even know the UK had a space industry at that time. Wasn't aware that there were any companies that you could move into to do space stuff. So I went and studied for 2 years forensic science. And it just so happened that one day, going through the internet, I found that there were companies in the UK that did space. And I came across Airbus as the first company. And that was my first exposure to the UK having a space industry. So I did have a nice tour of Airbus and got to go to the Mars yard. But it was at that point that I decided, I don't want to do forensic science anymore. It wasn't really a passion of mine. I did enjoy it, but I think I enjoyed more of a social side of it with my people I did the course with. So I decided there and then to do engineering instead, and stayed at college for another couple of years, did a engineering course, which then set me up for going to University of Plymouth for studying mechanical design and manufacturing. And then at the end of my second year, we were encouraged to go find a company to go do an internship with, a year in industry. And I went all the way to Birmingham to this engineering event to try and find a company which would hire me for a year. And it just turned out that there was a section of that event dedicated to Cornwall manufacturing and Cornwall space companies, who put me in touch with lovely people at Goonhilly. And I have been here ever since, from starting an internship, and that was nearly 5 years ago. And I've been involved in the Goonhilly 6 upgrade behind me, getting that from its old use from a geostationary antenna up to the world's first commercial deep space antenna, and being a part of the operations team to drive it every day, and getting involved in the upgrades that we're still going to be doing, and adding cryogenic receivers, and merging what I was fortunate enough to do with my degree, which was studying how to design and manufacture cryogenic receivers to hopefully go in the dish that I use every day.
Oh, brilliant. I mean, it's so good to have different faces, different stories, and different journeys from people around the table. That we're just human beings that are like, these young people. We were like them once upon a time, making decisions for what we thought were made for the rest of our lives, and actually just for the next few weeks. And here we are. And something you don't need a 10-year plan. You don't need to aim towards a 10-year plan. You can just take opportunities as they come and see what you enjoy. So thank you for giving us that insight. I've been quietly monitoring the questions that are coming in. And there's some really interesting questions, and we have got time for questions. So I'm going to have a look through, and I've got a few that have popped out to me that I think I might chuck at our guests. So no real gotchas, but one of the questions came in was about fixing a rover. Can a rover repair itself on Mars? And I was thinking to you there, Barry, in terms of the PanCam that you're building and is being tested. What happens if something breaks or something stops working on that PanCam whilst it's on the surface of Mars? What can you do about that?
Yeah, it's a really good question, and it's something we worry about a lot. As it said, once it's on Mars, there's no fixing it anymore. There's no going back and just swapping out a camera or replacing anything. And so right from the beginning, we kind of decide what sort of things we want to make redundant. So quite often that's our main way to almost have backups. So in case like we have a power converter, and if one of those power converters fails, then we can switch to another one and use that one. And that way it kind of extends the life. And so in the rover, it's because it is so kind of weight constrained, it's a bit of a balance of how much redundancy you have versus how much, how low mass it is. Because every time you have something that's just a backup or a spare, you have to build the thing again and have two. And so with PanCam, so if we go back, so whilst it's great and we want to use all three cameras, we could in effect get away with, if one of them was to fail, then we'd just rely on the other one that was available. And if one of the filters wasn't working, then there is a bit of duplication in there. So there's another filter in there that does the same job. And so I think it would be a kind of clever operations that would make sure we're using the things that were still working properly and then try and work around it. But ultimately, I think it's kind of through design, we really try and make sure that if things were to fail, it might just be temporary. And then the next day when it's a bit warmer, it works better.
Yeah, and there's some great examples out there as like Spirit and Opportunity. I think they were made to work on the surface of Mars for around 90 sols, wasn't it? And Sol being a Mars day, and Opportunity went on for over 10 years. Just with the engineering built into getting it to last for 90 days meant it went on and on and on, and they kept operating that rover on the surface for as long as they could. And I'm hoping that with ExoMars we'll do the same, and we'll keep going with that thing for as long as we can. And you guys will be a part of it, not necessarily in a bad way of having to try and fix things, but certainly keeping that rover going for as long as we can. Thanks, Barry. There's a question, and I'm jumping the topics a little bit. There's a question about testing spacecraft for other planets and whether gravity is a consideration. Now, Charly, I'm going to hit you on the spot with this one a little bit. We've talked a little about testing spacecraft for space and launch, but is there any consideration with regards to sending something to another planet with regards to like the gravity or the atmosphere that's there, and how do you do that testing on Earth?
They do normally what happens. So again, if it's going to another planet, when you've got then the kind of, again, the main things are, it's, as I said, there's launch, but then you've got to deal with going back through the other planet's atmosphere and landing. And what will get done is some very clever people, of which technically I'm meant to be one of them, will do a lot of simulation work. So we'll kind of make a very detailed model and then do sort of simulations to see kind of the forces that will get involved. And then, being engineering, one of the big things is we make models that are rough approximations of a situation, then we shove a safety factor on, just to kind of cover all the various things, because you cannot account for absolutely everything because otherwise your model would just, even with the biggest computers, it would just take years and years to run, and probably years to build the model up. But you said, yes, you kind of just kind of try and guess, obviously with a lot of sort of mass involved, to try and work out the forces and accelerations that would be involved. That then gets boiled down into a test specification, so that when that sort of equipment comes to a test house, it will be kind of made sure that it's all, it will kind of be covered with the eventuality.
So which part of a mission life cycle is the most tricky then with regards to the shock and vibration environment? Is it the launch or is it the land? It's the launch, is it?
Absolutely.
So strapped to that rocket.
I mean, yeah, because particularly as if you're going through the Earth's atmosphere. I mean, I can't say for certain, but from kind of my knowledge is the Earth's atmosphere, obviously going through that, it's a lot heavy, it's a lot sort of denser. So you've got sort of more things. Obviously, the landing, because they make that, they obviously the designers, sort of Barry says, they're designing to make sure it's not crash landing. Although obviously some, depending on the mission, it might crash land. There have been instances of that, trying to break through the surface. So in that situation, probably that would be the greatest shock. But again, you're sort of testing for that. But on average, it probably would be the launch, having to go through on the massive rocket.
Yeah, and another question then following on from that, then I guess if someone builds a satellite or a spacecraft and they've spent lots and lots of money, lots of time building that spacecraft, and you bolt it to your turbine, are you exposing that spacecraft to the exact same environment that it would see in flight, or is it a level of that?
That is an interesting point. It is an approximation, because pretty much with direct testing, with one exception, we sort of take what is a 3D environment. So when it's on a rocket, it's being shaken in all directions at once, and putting it on a shaker, which can only do one at a time. So it tends to actually over test, because you're wanting to make sure it's a kind of a building those test specifications is quite important, because you don't want to overdo it and break it and put unnecessary stress, and also to make sure it survives the test on the ground, then it has to be stronger and heavier, which means it will take more rocket fuel. But you also don't want to under test and then it break. But there is one exception as far as the kind of only testing one axis is we have an acoustic test, which I haven't mentioned, which is just blasting sound, and that does, obviously the spacecraft sees all of that in one go. But they tend to be kind of, it's noise, and you only do that for every something that's very big, and sort of particularly that has an effect on solar panels, because they are very big but very light.
Brilliant, and I guess it really gives an insight into how much work has to go in before that rocket launches off the pad with the payload on the top of it. How much has gone into that point? People think about that being at the start of the mission, but I like to think it's around about the middle when something launches, because there's a whole load of work before and a whole load of work coming afterwards. And that takes us on a little bit, I guess, because looking at the time, I want to get a question to Jamie, and I want to reframe a question and sort of follow on from you, Charlie, into how difficult it is to get a rover to Mars, but not that question specifically, Jamie. It's I'm thinking more about your part of this. Okay, we've built and tested a spacecraft. It's now in orbit around Mars. How difficult is it to operate a spacecraft in orbit of Mars? I guess there's a lot of factors that have to be aligned where you can even see that satellite from where you are on the Earth and send data to it.
Yes, there's a lot of work that even before it gets launched, what we have to do here at Goonhilly, we have to do mission readiness testing to make sure that we're competent, we know what we're doing, these settings all work in a safe environment before we're unleashed with an actual spacecraft. So before launch, we spend weeks and months training the staff here, the operations team, creating all of the scripts and the macros which go into configuring Goonhilly 6, configuring the station itself, making sure all of the switches are in the right place, all of the electronic routings in the correct place to get that signal from the actual antenna through to the modem to be able to send that data onto the customer, and then making sure that we've written all of our procedures so that we can do all the steps in the right order, so we don't accidentally radiate the spacecraft with too much power, or we don't put in the wrong data, so we're downlinking the wrong kind of telemetry or the wrong coding type. So
that's brilliant. I mean,
massive amounts of work goes into preparing it, but for actually on our first day, a mix of nerves and then making sure we're testing everything we've prepared for. We're lucky we have a satellite simulator here, so we can test that spacecraft being there without actually having a spacecraft to make sure that the ground to space link is all working. We can demodulate all of the right telemetry and send all the right telecommands out, and we get the right responses back from the simulator. So once we get onto our first pass, there's an element of nerves and pointing the dish to it, and with a little bit of luck, it all falls into place. We downlink the data, the customer's always very happy, and we've done our job right.
That's amazing, and I really, I guess it goes to show we see lots of space in the mainstream now, lots of space being reported, and there's an element that makes it look easy, but I guess hopefully that there's some insight here into actually how much work, how much effort, and how much people have an impact in these things, and how hard people are working on these missions in the background. Astronauts get a lot of the plaudits, but actually there's a lot of people working in space that aren't astronauts themselves. So I'm going to end there and thank the panelists for joining me and talking to me, answering my questions, and hopefully they've given you, the audience, some insight into careers in space. Do stay on this call though, audience, because the next panel coming up is Maths in Space. It'll be starting very, very soon. You don't have to do anything. You just have to stay right where you are. Thank you very much, and I hope you enjoy the rest of your Mars day.